go ahead and get doing some mechanics. All right. I'm still working on all this grading, and I'm so bogged down with your grading that I don't want more grading, so stuff won't be due till a week from Monday. All right. But I'll try to have all your grading done for Monday. So let's go ahead and pick up where we left off last time. All right, so we were talking about how the nice thing about energy, wherever you can use energy considerations, is that, does anybody remember what's nice about it? It's a scalar thing. So as a result, if you can get an expression for energy as a function of something, you want to use that. And in the case that you have one dimension, meaning mathematically one dimension, meaning that location depends only on one variable, then you can actually use that to solve for motion, which I illustrated last time. That's handy as well. And so it can take some really complicated systems and turn them into things that are soluble far more easily than we thought before. So another example of a curvilinear system would be this object that's supposed to be a wire that's all curved in 3D. It's supposed to be taking up all sorts of space. But in terms of the location of a bead on that wire, that can be described with a single variable, which is s, the distance along the wire. And in that case, I have an expression for the kinetic energy of that bead, which is 1/2 m s dot squared. Okay, and I can also note that the tangential force on that bead, that just means the tangential component of the net force on the bead, is equal to, must be equal to m times the second derivative of s with respect to time. All right. So this is a nice way to analyze the motion. In this case, we have sort of a constrained three-dimensional object, which allows us to treat it as to determine location with a single variable. So we call it a one-dimensional system nonetheless. All right. So in this case, if all the forces on my beads, tangential components, are conservative, clearly the bead's not allowed to move off of the wire, so all those components, there can be no work done by components of forces that are perpendicular to the wire because it won't move that way. And so as a result, if all the tangential components of all the forces on my bead are conservative, then I must have that this is a system in which mechanical energy is conserved. So I'll say if all the forces on the bead have tangential components that are conservative, then clearly no non-conservative forces are doing work, and we would say in terms of physics speak, I'll just go ahead and write it all out. No non-conservative forces do any work. Another phrase for that is that the system is isolated energy-wise. And mechanical energy is conserved. So we can apply all the things that we learned last time, all the relationships that we found, including the one in which we were able to solve for motion using energy considerations. All of those will apply to this system. All right. So, what else do I want to say? I think that's all I want to say. I can also, in that case, write potential energy as a function of that one variable. And once that should be possible. And in that case, if I had that maybe as an analytical function, then the tangential net force on my bead must be equal to minus du ds. And what else have I got? I guess I'll go ahead and write this in symbols. Mechanical energy, which is E, which is T plus U, would be equal to a constant. And wherever U is a minimum, we would have a stable equilibrium. Wherever U goes through a maximum, we would have an unstable equilibrium. Everywhere else, minus du ds will be equal to the tangential force, the force along the bead on the object, the net tangential force. And I think that's all that we really want to say about these types of systems, except that you can also then use I wrote that for you guys, but I didn't write it in the notes. Hold on just a second. We can also use that T is equal to E minus U as a differential equation S dot squared, pardon me, U of S. And I can solve this firstly for T as a function of S, and then go on to solve for S as a function of time. Those are the things I want you to remember about energy for the one-dimensional system. And remember, one-dimensional in that case means mathematically one-dimensional, such that location can be determined by a single parameter. Okay, let's do an example. All right, so the example I want to do is a classic. It's an example of a system that looks complicated, as your author says, but can actually be treated as mathematically one-dimensional. And it is also a system that is isolated energy-wise. So the example we're going to work on is the stability of the wooden cube balanced on the hard rubber cylinder. Okay, so let me just describe this situation for you. I have I'm going to look sort of cross-sectionally down a rubber cylinder, and I describe it as rubber, meaning that it will have sufficient static friction that the object on top of it will not be allowed to slide. And so maybe initially I will have sort of a cube. Oopsie, that doesn't look like it's sitting on top, but it should be. A cube that is initially sort of sitting on top of my cylinder. Sorry, that doesn't look like a very good drawing. Okay, so initially I've got a situation like that. All right, and I'm going to call the radius of the cylinder R, and I'm going to call half the length of one side of the cube, I think we call that B. Okay. And then what I'm going to think about is that a stable equilibrium for that object? And the way to figure that out is to perturb it a little bit from its stable point and then see, well, you can do it a couple of ways. Experimentally, will the object go back to its original orientation? Or will it continue to go farther and farther if you disturb it? And another way to think about that is mathematically, if you disturb it, that means that you sort of take this arrangement and perturb it a little bit, changing some sort of in this case it would be some sort of an angle, which if we push it over to the side here, we'd have an angle involved there. If I were to change the angle of this box, what will happen to the potential energy as a function of that perturbing angle? And if the second derivative of u with respect to that angle is positive, then I know that I'm going through a minimum, right? And that means it would be a stable equilibrium. And if it's negative, then I know I'm going through a maximum, because I know at this position, just by symmetry, this must be an equilibrium position, right? Okay, so let's go ahead and do that. So I'm going to examine the cube's potential energy to find out if this equilibrium point is stable or unstable. So I'm going to imagine this situation now. I have the cylinder is here still, but I've sort of pushed the block just a little bit. The cube is pushed over just a little bit. So that as a result, instead of having this contact point here, its contact point might be over here, in which case I've moved sort of that far along the cube because it went without slipping. So I only have about this much of the cube left. The rest of the cube is sort of over there. Not the best drawing, okay. Okay. So there's my perturbed situation. And let me draw what I want to think about here. So I will now have a different contact point between the cube and the cylinder. And I'll say that the angle, because before the contact point was directly above. So I'll say this angle by which I have moved that contact point, that's the thing I'm going to call theta. And clearly the line of the cube is tangent to the curve of the cylinder. So if I continue on in that line, I'll go straight up into the cube, parallel to the sides of the cube. And if I imagine over here is like the center of the cube, then let's just sort of call some points here. I'll call this point down here the origin. I'll call this point here, where it reaches sort of that central line on the cube. Let's call that point B. And then I'll call the center of mass of the cube point C. All right. So the thing that I want to do is I want to express the height of the center of mass of my cube above the center of mass of my cylinder in terms of theta. So let's go ahead and sort of on my figure. I'm going to call that thing H. All right. So what is H? Well, I've got this line here, whose overall length is the radius of the cylinder plus the variable that I called B earlier. And so H is going to be, let me see if I got a red marker. This vertical distance here, plus another vertical distance. Let's see if we can figure out that vertical distance first. So H is equal to, well, I've got a right triangle here whose hypotenuse is R plus B, and this angle here must also be theta by interior angles. So it is R plus B times the cosine of theta. You guys see where that expression came from? Okay. And now I'm going to take this limit where theta was very small, because this is going to be the place where I'm going to want to consider that second derivative. So I'm going to take theta very small, in which case this line here can be considered equal to how do I say this? is going to be equal to this length here. For small angles, those two will be equal. All right. So in that case, I have r theta is that length. I only want the component of it. That is up and down. So here's also theta in there. Again, because of mutually perpendicular sides here and mutually perpendicular sides here. So the angles between them must be the same. So then I have r d theta times the sine. I'm sorry, r theta times the sine of theta. And I think that's what, okay, that's the expression I've got for h. Okay, so in this case, which again holds for the small angle limit, but that's okay, I only need it in the small theta limit, because all I want is I want an expression for u as a function of theta, so that I can then get an expression for du d theta as a function of theta, and then therefore get an expression for d2u d theta squared as a function of theta, and determine whether this function is positive or negative when I evaluate it at theta equals 0. Oh, I'm off the page. So I'm going to leave these steps to you. And by the way, once you have this, you will tell me whether it is stable or unstable. All right, so why don't you guys break yourselves into 2 groups of 3 and work that out. Are you guys okay with what's up here right now? Logan, are you okay with what's up there right now? There's a couple of subtleties, but if you want to ask what I can go ahead.
Start off with gravitational potential energy, so you use GH, and then just plug it on. Yes. plus our design rate.
So if R is much larger than B, then it would be
So you
stable.
get our theta cosine theta minus B sin theta.
Because anything else is
Yep. Times mg, of course.
Yeah.
And so I'm just taking the derivative of that one more time.
Well, let's see if we get it.
All right, so get a condition for which this is a stable equilibrium. Are you guys working together?
We put each other on the path together.
Good. All right, so get your conditions for stable equilibrium. And your conditions for unstable.
Considering gravity to be negative. No? Okay.
I was trying to figure out how we got R minus B, but I consider theta to be B. That is the point of equilibrium.
Yeah.
Because what expression do you get for second derivative?
Okay, so you have minus B cosine theta,
Uh-huh.
and then minus R theta sine theta.
Plus R cosine theta, yes. That is what I got.
This was the step that I missed.
But they were evaluating theta equals
Oh, they
zero.
already evaluated it?
Yeah.
Okay, alright.
So, at what, under what condition would it be stable?
That would kind of make sense if you think about it. This whole small
Yeah,
on something
zero.
big. If
Okay.
you move that small something, it's not going to just be
I guess just zero.
the big.
I could do this with,
That's
Yeah.
sitting on.
that was mg
Now,
times
if
R
something's
minus
really
B.
big on something really small. A little shift. It's like a fulcrum at that time.
Yeah. Right.
Yep. So, at what condition would it be stable? If B is less than R,
It's like
would be possible.
trying to
We can remax
balance
on
a board on the
Yeah,
So
so,
we're looking for one
Are you ready?
It's not though. It's not though. I mean, there's people out there
All right.
that balance giant boulders on tiny little things all the time.
So I'm going to go ahead and start working here. Again, I feel like the thing that I did worst in this is noticing that as it sort of got perturbed, it didn't slide. So as a result, it was rolled over. This point here was rolled over by a distance, this point of contact, r theta, and that was also the distance by which the object was therefore moved from its center line. All right, anyway. Okay. So I'm going to go ahead and we already have this sort of down to math here. So u as a function of theta will just be mgh, where h is r plus b cosine theta plus r theta sine theta. And du d theta will be mg. And I've got r plus b times the partial of cosine theta with respect to theta, which is negative sine theta, plus r times the partial of theta with respect to theta, which is 1, so I get times the sine theta. So the derivative of the first times the second. Now I need to do the next, which will be the first times the derivative of the second, so that'll just be r theta times cosine theta. All right, so that's what I've got for du d theta. Let me check with my notes, make sure I'm okay with that expression. R plus b minus sine. Plus that. Okay, I think everything's okay there. All right, so now I'm going to, from this line, I'm going to do a little bit of simplification. Du d theta is equal to negative r sine theta plus r sine theta, so those two will cancel, so I will get mg times negative b sine theta plus r theta cosine theta. Okay, now I'm ready to get my second derivative of u with respect to theta squared. So I've got mg times negative b cosine theta, taking the derivative of the first term, plus r cosine theta, taking the derivative of the second term, just multiplying by r, where I'm taking the derivative of this object times that object, doing the product rule thing, plus r theta negative sine theta. Are there any questions about that math there? Okay, cool. Okay. So now I need to evaluate that second derivative in the limit where theta is equal to 0, because around this orientation. And I get that it is equal to mg times r minus b, because cosine theta goes to 1 and sine theta goes to 0. Okay, so in this case, it depends whether it's positive or negative. This will be a positive number if r is greater than b, which will lead to a stable equilibrium. And it will be a negative number if r is less than b, which will be an unstable equilibrium point. So what that means, and basically what we're looking at here physically, another way to look at that is we're trying to look at this new location for the center. Is it above or below where it was before? Did I go up in terms of my potential energy, or did I go down for that tiny perturbation? You guys, you follow? You agree with that? All right. So, and the answer is it depends. It depends on the radius of this thing. All right. So if the radius is bigger than half the width of the cube, then this will be a place where I've got a stable equilibrium. So if in this position, if I give it a little tiny nudge, it'll come back to its equilibrium point, right, and oscillate about its equilibrium point until it's able to dissipate a little bit of energy. However, if this radius is smaller than half the width of the block, then that will be an unstable equilibrium. If I give it even the tiniest nudge, it will just go faster and faster away from that point. Okay? All right. So this was an example that is just kind of, well, I mean, it's kind of fun because it's so mechanicsy. It's a great system that we can think about, that it looks like it's a three-dimensional thing, and it looks like it's a very complicated thing, but mathematically it is one-dimensional because its location depends, the position of our system depends on one variable. So mathematically, this is a one-dimensional problem, and it's actually quite easy to solve as a result. Okay. All right. So let's move on. There's lots of other one-dimensional systems that don't look one-dimensional. I'm going to tell you about another one that's kind of classic. sometimes we have objects that are moving in three-dimensional space, and maybe we have multiple objects in our system, but because they are constrained in some way, we can treat the system as one-dimensional mathematically. So an example of this would be constrained systems of multiple particles and a common example of this would be the Atwood's machine. Okay, so, but it won't just be the Atwood's machine. You'll also want to keep this in mind if you ever have a system of multiple objects that are connected by strings. Or struts. That means whenever you have a string, we're going to assume that the string cannot stretch, and therefore there's sort of a constant there in terms of the length of that string, meaning many times the distance between two objects. Okay. So in this case, we can, even though we have a very complicated system, sometimes describe the system's position in terms of one variable. As a result. Okay, and so if that's the case, we describe it as a 1D system. But clearly it would be taking up 3 dimensions of space. So the example of the Atwood's machine, just remind you what an Atwood's machine is. An Atwood's machine is a pulley connected with a pulley sitting on a frictionless axle. And then I might have one mass hanging off of this side and another mass hanging off of this side. All right, and let's say that over here, I'm going to make a coordinate system down here. So that M1 is at Y1 and M2 is at Y2. All right. So in this case, I am going to have, let's remember for an Atwood's machine, I'm going to have a frictionless axle. Your author even says that it's a massless pulley. We don't have to do that, though, so I'm not going to make a point of that. But I am also going to say that this string must sort of stick to the pulley, meaning that it can't slip along the pulley. All right. And so what happens that in terms of forces is we've got a couple of things happening. I mean, if we could talk about it the way your author talks about it if you want to, but in the case of what your author talks about, just to be clear if you've read that, this is a massless pulley. So as a result, there's no rotational inertia to it. And as a result, the tension in the string is the same everywhere. So if you were to evaluate the forces on our system, we've got a tension upward on this mass, a tension upward on that mass. We've got a weight down on this mass, and a weight down on this mass. I should have drawn that as a free body diagram. I'll call that T. T2. I'll draw a free body diagram for this one. M1G, T1. And because this axle is massless, it can instantaneously get to the orientation where the two tensions are equal. So the T2 will always equal T1. And then we have some forces along here, along this surface. We'll have a normal force that is out on the string. We'll have a friction force that prevents, let's say M2 is heavier than M1. We'll have a friction force that prevents the string from slipping along the axle, causing the pulley to turn. But so long as there is never any slipping, this friction force never acts through a distance, because there's no relative motion between the two. And so neither of these forces do any work. In the case that T1 equals T2, those are equal and opposite forces acting through equal distances because the string confines them that way. And therefore, the positive work done by the tension in the string is always equal to the negative work done by the tension in the string. All right, if you guys can follow that hand-waving argument, there's no place here for energy to enter or leave the system. All right, so this is a system that is isolated energy-wise. Now, if we go to the case where the axle does have some mass, then yeah, we can have these two tensions, but then we would also have the forces acting here. I'd have T1 down, because that's where the tension is, a pull in along a string. That's what a tension is. And I'll also have a T2 acting down here. This is still my free body diagram. Now, for an extended object, when you draw a free body diagram, you draw the forces where they act. Okay. So I have T2 acting here. And if T2 is greater than T1, that's all well and good. That just means there will be a net torque on your what's the word I'm looking for? Pulley. And as a result, it will change its angular velocity. So that means that there will be some work there, but that will result in the change in the kinetic energy of this pulley, which will be opposite to the works done by the forces on the other side. Okay, so let's just do that in a hand-wavy way if that's okay for you. It's still isolated momentum-wise. All right. Okay. I'm sorry, isolated energy-wise. Sorry. It's just now we would have to have the energy of our system. Let's just go ahead and write this in symbols so I can get back from all this hand-waving. Isolated energy-wise. So my mechanical energy of my system will always be a constant. And in some cases, you can think of this as, in the case that I have a massless pulley, this would just be the energy of object 1 of mass 1 plus the energy of mass 2. Wherever I see energy, I need to think Ke plus Pe, where Pe is mgh. All right. But in the case that my pulley isn't massless, then I also have to have the energy associated with the pulley, which the reason that your author leaves it off of there is because we haven't derived that expression, but those of you who've been in 240, 250, or any calc-based intro knows it's 1/2 I omega squared. All right, so this is another system in which, you really could uniquely, if let's say at one instant you said, I'm going to call the orientation at that instant 0, then as it moves from there, you can just describe the subsequent positions of your object just with some angle theta relative to that. So this really is a one-dimensional, mathematically one-dimensional system, because you can completely describe its position with one variable. All right. So I don't want to spend too much time on that, though, because it doesn't warrant it. Oh, and I don't have it. I want to talk about central forces. This is a super long chapter. All right. So central forces, again, we're going to be talking about a situation that it takes up 3 dimensions physically. But hopefully we can get it down to a one-dimensional problem mathematically. So can we get it down to one dimension mathematically is the question. All right. If we could, that would be great. So let's first talk about what we mean by central forces. A central force is a force that is, you know, maybe some function of location. It could even be a function of time as well, but for right now, we're just going to think about a function of location, such that it has some magnitude of its force, that's like so, and the direction of it is always radial, meaning straight up from the origin. And in the case that this function of location was a negative number, that would be an attractive force. If it was a positive number, that would be a repulsive force. So an example of a central force would be the electrostatic force that we express with Coulomb's law. And so let's remind ourselves what this expression is for. This is an expression for the force on a charge lowercase q that is in the field of a source charge capital Q, and I'm making the origin of my coordinate system the location of that source charge capital Q. So right here, at my origin of my coordinate system, I've got a charge capital Q, so there's my origin. Now to make this a right-handed coordinate system, I go x, y, z like that. Okay, and then I've got some point out here, P, where I've placed another charge, which is lowercase q, which represents what we call a field charge. We would call the capital Q, in this case, the source charge. It's the source of the electric field. And the lowercase charge q, the field charge, it's in the field due to the source. Okay, and it's located at some location R. Okay. And just to be clear, I'll draw its projection into the xy plane to be clear that it's kind of an arbitrary location. All right, so in that case, I have the case that I can express my force like this. There are a couple important things we should know. The first is this force is conservative. We've already proven that. Granted, I did it for the gravitational case, but it's the same proof. What do I say? And the second thing that we should note about this force is that the magnitude of the force does not depend on theta or phi, where I'm going to talk in spherical polar coordinates for a minute here. We're going to call that angle there theta, and the angle that the projection makes relative to the x-axis, I'm going to call that phi. Notice that in this expression, there is no theta or phi dependence. There's no dependence on anything except distance from the origin, which in spherical polar coordinates we call r. Okay, so there is no theta or phi dependence. And when that is the case, we say that it is spherically symmetric or rotationally invariant. Those are equivalent statements. Okay. And the thing that we're going to start with next time, which is very, very important, and by the way, we can write the second thing in terms of f of r is just equal to f of r. Notice there's no theta or phi. The thing is, condition 1 always holds if and only if condition 2 holds. That means if 1 holds, then 2 must also hold, and if 2 holds, then 1 must also hold. This is an important proof that's going to have to wait till next time, so we will prove it next time. Good work today. You all did a good job. You did good work today. Everybody got it. What's up, Cash? Let me shut off my recording first.